Alright, now this is a video about the concept of convection and in heat exchangers. Okay, this is in particular to the module of in-vehicle systems MM0312. Okay, students taking Thermal 1 or Thermal 2, you do not have to regard this. Okay, this is more about Thermal 3 topic of convection. Okay, so for the DES students who are currently taking the in-vehicle systems, okay, this part on convection, I'm just going to go through the very basic of how to approach a typical problem of heat exchanger, okay, and showing you the workings for the first question in the tutorial. Okay, so before we begin, let's establish some concepts first. You will have two fluids, okay, a hot and a cold. Okay, in this case, the cold will be traveling in the inner tube, and the hot will be the one wrapping around, will be an annular wrapping around the inner tube. What happens is as the hot liquid comes in, it will lose the heat to the cold liquid. Okay, and as it comes out, the hot temperature will be lower. The cold liquid will go in and it will gain heat from the hot and it will come out at a higher temperature. Okay, so if you look at the temperature distance graph, right, this is what's going to happen. For this case, this is a parallel flow, meaning that they go in and come out in the same direction from the left to the right. Okay, so this will be the case. You'll have a hot in and hot out, cold in and cold out. And you define delta T1 and delta T2 as this and this respectively. Okay, and from here you can get your LMTD, your log mean temperature difference, which is delta Tm. Okay, according to your lecture notes, it is delta 1 minus delta 2 over the natural log of delta 1 over delta 2. Why is this so important? Why is this delta Tm so important? So that you can calculate for the heat transfer rate based on this equation. Okay, UA delta Tm. Okay, we have previously established that UA is actually the inverse 1 over sum of resistance. Okay, if you look at the lecture notes, the more descriptions were given to you. So the delta Tm, you have found it. The A is the contact, is the interface area between the hot and the cold. So for this case, the interface area between the hot and the cold is the tube cylinder area itself. Okay, it's the tube cylinder area itself. Okay, I've drawn it over here. So this is your A. Okay, internal radius times pi and multiply by the length of the tube. And this is what you get your A. Now the only unknown here will then be U. Okay, this transfer coefficient is effectively actually equals to 1 over U is equals to 1 over inner liquid H plus 1 over outer liquid H. And by right, it should have the thermal conductivity of the pipe material itself. But a lot of times, your pipe material is considered to be thin and very conductive, and thus providing you with very little resistance. So it can be considered as negligible. So you can consider just these two terms. Okay. So now in order to find Q, you need to find U, which is based on HI, inner and outer. Okay. So inner is usually what we see. The question will usually pose it as water, okay, which is the cool water coming in, and it will gain heat and go out at a higher temperature. The outer is the one that's supposed to heat up this water and is a hot liquid over here. A lot of times H0 is given to you. So the issue is always, the more mathematical calculations are involved is in finding H in the inner liquid, which is water. Okay, how do you find it? Because looking at the inner tube, you are going to have a different temperature across. Okay, so we need to have a typical temperature called the bulk temperature to carry on with any calculations. So how do you calculate the bulk temperature? It is basically an average of these two temperatures. Okay, C out in plus C cold in plus C cold out divided by 2. Okay, bulk temperature is the average of the in and out of the cold liquid. Okay, and from there you will have a certain temperature. Okay, so for example, I managed to find that the bulk temperature is 40 degrees. So what do you do next is you go to the steam tables, because this is water. Go to page 10. Okay, page 10 of your steam tables, further properties of water and steam. And you go straight to your bulk temperature. So if my bulk temperature is 40, I will have all the values over here. Okay, my CPF is this 4.179. Okay, my specific volume will be this 1.10079. Okay, my μF 651, my KF 632, and my Prandtl number will be 4.3. Okay, take note that you're only taking the F values, because right now your cold water is at liquid state. The F stands for the saturated liquid values. Okay, so you only take the F values, don't take the G values. They stand for your dry steam values, which are not here. Okay, so based on these values that you find from the steam tables, okay, you can calculate for Reynolds number, Prandtl number, and from these two numbers you can get a Nusselt number. Okay, using this Nusselt number, you equate this number to Hi times diameter over Kf. So this Hi is the unknown which you will find. Okay, because you have this, you only do not have Hi. You found it, you put it inside, you can find your U. You found your U, you can find your heat transfer rate across the heat exchanger. Okay, so this is the flow, how the problem flows. One last thing is that as you look at the heat exchanger, you have a hot liquid and a cold liquid flow. You can actually, and you're going to have temperatures, okay? T hot in and T hot out, right? Same T cold in and T cold out. You can actually find the heat lost by the hot liquid using this formula. Okay, because from thermal 1 you know that Q is equal to mCp delta T. Okay, so you have a mass flow rate, you have your Cp delta T. You can find the heat lost by the hot liquid. It should actually also be the same as the heat gained by the cold liquid, because you see, after all this whole flow, right, the heat exchanger is only between the hot and the cold. Where the hot loses is where the cold will gain. So the cold will also be mCp delta T. Okay, and actually QC and QH are the same. And in fact, these two are also equivalent to the heat exchange rate across the heat exchanger, okay, which we have previously sought to find out. So everything closes in a loop, and we shall show an example about on this. So you go to tutorial 1. Okay, tutorial 1, question 1. Which is this lah, okay? Question 1. It's not the part A, but the part B. Okay, question 1. And the question is this. Okay, you have a double pipe, meaning this configuration. Okay, so the oil, right, is at the annular. Okay, annular. This means the outside lah. Okay, oil is here. And cooling water is inside. This is water. Okay, so the oil has 120 degrees coming in and drops to 75 as it goes out. Okay, and the cooling water comes in at 25. But the question is, you do not know what is T cold out. Okay, and you have the mass flow rate of oil 680 kilogram per hour, and the mass flow rate of water 500 kilogram per hour. Okay, the bore is 50 mm, means the diameter is 0.05 meters. Okay, and the heat exchange coefficient between the oil and the pipe is actually H naught, 2200 watts per meter square Kelvin. Okay, and between the water and the pipe is actually the inner liquid, right? The inner liquid is the water. Okay, so the H in is 5800 watts per meter square Kelvin. The specific heat is Cp of oil 2200 joules per kilogram Kelvin. The specific heat of water 4200 joules per kilogram Kelvin. Okay, so you are supposed to find the length. What is the length? Okay, so let's just draw the temperature profile first. Because they are parallel flow, okay, they come in from left to right the same. So you're going to have something like this. This is 120, this is 75, this is 25, and this is, you don't know, TCO. Correct? Well, the first off is that you know the Q lost by the oil is the Q gained by the water. Okay, so it's m dot oil Cp oil delta T oil equals to m dot water Cp water delta T water. Okay, 680 times 2200 times 120 minus 75 equals to 500 times 4200 times T cold out minus 25. Okay, so this is how you do it. A balance between the hot and the cold. The heat loss is the same as heat gain. Okay, so you will find that your T cold out will be 57.1 degrees Celsius. Okay, because you find this, you are able to find the log mean temperature difference. Okay, so this is 57.1, right? So delta T1 is 120 minus 25, which is 95. Okay, minus 75 minus 57.1 will give you 17.9 over natural log 95 over 17.9. Okay, so the delta Tm, right, is actually 46.2 degrees Celsius. Okay, now you have one number here. You are able to find for the heat exchanger, which is U A delta Tm. Correct? U is if you can see, U is 1 over U is 1 over H plus Hi plus 1 over H naught, the inner liquid and the outer liquid. Okay, and you are given Okay, you're already given the outer liquid and the inner liquid H. So actually you don't have to go through a lot of calculations. This is given to you. Okay, so it is 1 over H in plus 1 over H out inverse. Okay, because of this. Okay, I need to inverse this, so I'm inversing this. Okay, and the area is the area of the inner pipe. Okay, the area of the inner pipe, which is the pi times diameter times the L. Okay, pi times 0.05 times L. So this area, this is U, and I have 46 times 0.2. So this is the whole thing. Okay, like I said just now, Q cold is equals to Q hot is equals to Q heat exchanger. Okay, you can just use any of them, either cold or hot. Okay, so for me, I can use the hot, which is the oil, CP oil, delta T oil. Okay, which is so now this everything is in SI unit now. Okay, please don't be confused, because this, although we say this is degrees Celsius, right, but actually it is a delta T. Okay, it is a temperature difference. LMTD is a log mean temperature difference. So whether I mean the interval between of degrees Celsius is same as the Kelvin. So it is effectively also 46.2 Kelvin. Okay, it is a delta T. So this number should be used. Okay. And what we're gonna do is use SI unit 680 over 3600, right? And you have the CP of oil as 2200. Okay, and your temperature difference is 120 to 75. So this equation is equals to this. Okay, and you know that HI is 5800, H naught is 2200. So the only unknown is this one, L. Okay, using this equation, you should be able to find that your L is 1.62 meters. Okay, so there's the second part to this question, because right now the configuration is in parallel flow. If it is counter flow, means one going the opposite direction of the other, then what will the length be? Okay, assuming all the temperature do not change. Okay, I will leave it to you to find out, and I shall end my video here.